see what's going on here. I have a few things I'd like to do. I don't know how much of this we'll get done in a half hour. Well, we'll do what we can. This is my original plan when I figured, oh, I'll probably have about 45 minutes. You guys have some tough questions today. Okay? But that's okay. But I'm definitely going to be able to show you how to approximate an integral using this thing called the trapezoidal rule. That I know I can do. I'll also show you something better than the trapezoidal rule called Simpson's rule. I don't know how much we'll get into the errors. We'll see. Let's see how well this goes. Kind of depends. Now we'll see how time goes, and then we'll go from there. But here's the picture that I think, and this came from your book, but this kind of sums up what the trapezoidal rule is about. You guys remember when we divided into our subinterval, what shape were we using? Rectangle. And that's because if I use the left endpoint on this problem, I'd have rectangles that would be under the curve, right? And if I use the right endpoint, I would be using rectangles that are over the curve. So the idea is, hey, let's kind of use both endpoints. And we'll connect them by a line. And what I'll do instead is be finding the areas of these trapezoids. Does that make sense? You don't have as much error. You see that? That's the idea of this trapezoidal rule. So actually, you guys programmed that thing in your calculator. Remember you had right sum in your calculator? I don't know if you've done left sum. There's an exercise in this section in the book where you kind of put them together and you create the trapezoidal method. It's a beautiful exercise. I didn't assign it for the sake of time, but it's there if you're interested. Okay? Now, how does it work? Hey, this is the old game, right? Partition the closed interval into n subintervals, each of with delta x. B minus a over n. That's what we've been doing the entire chapter. Oh yeah, what's the area of a trapezoid? You guys know that one? Oh yeah. You're pretty much there, right? Area of a trapezoid equals. I mean, I guess it depends how you were taught. I was always taught that trapezoids look like this. But that's not true. I mean, that is a trapezoid, but it's misleading. Trapezoids can look like lots of things. What's the key feature of a trapezoid? One set of parallel lines, okay? So the trapezoids we're going to be looking at are going to be under a curve, and so it'll look more like this. The set of parallel lines is going to be here, okay? Now, what we used to call the parallel lines in geometry class, we used to call them base number 1 and base number 2. Did any of you guys do that? And then, do you remember the formula then? 1/2. That's what I thought you'd say. Yeah, we don't remember that. But actually, when I write it down, it might. Because what's the area of a triangle? Yeah, well, here you have two bases. So it's kind of a generalization of that. You guys follow that? So if I want to find the area of one of these trapezoids, well, what I need is the following. I need, well, 1/2. And then I'm going to need the sum of the bases. And then I'm going to need the height. Now, do you know what the height is for this trapezoid? The height is this black segment because it's turned sideways, right? The bases are you with me? Okay. So it's like the bases are f of xi plus f of, I don't know, I'll call it xi these 2 points are, if you compute f of those, that's the 2 lengths of the bases. Does that make sense to people? Now what about the height? Well, I called that delta x. But I told you on the last slide what delta x was. Do you remember? B minus a over n. Does that make sense? I don't know. Go ahead, Alex. Yeah, okay. That's because I didn't label enough. Here. This point right here. What are its coordinates? Well, let's call the x-coordinate x sub I, because I'm going to say that this is the ith subinterval, kind of like the 4th subinterval or 5th. It's just whatever number I'm at I. Does that make sense? Okay. And then the output of that, the y-coordinate is f of xi, because the height of that thing, it goes all the way up to the function. Okay, so that's this point. And now the other point, well, I don't really know what it is. I'll call it xi plus 1 because it's 1 more. And so then it's f of xi plus 1. And so if I say, what's the sum of the bases, well, notice it's the y-coordinate. Does that make sense? Okay. Now, if you want to compute the approximation for the area under the curve, what do? Well, we're going to do it this way. The area under the curve, say from here to here, right, from A to B, the area under the curve is going to equal, well, I'm going to have to add up a whole bunch of trapezoids together. Does that make sense to people? Now, what's my symbol? There it is. That says I'm going to add. What do you think I'm going to put on top and bottom of that sigma? I equals 1 to n. That's right, because we divided it into n subintervals. We've done this a million times now, right? And so what I want to add up are a whole bunch of these, right, these areas of the trapezoid. That goes in here. I just don't feel like writing it. Well, I almost do. Let me say something about it. Did you notice that you can bring some stuff out in front of the summation sign? What can you bring out front? The b minus a over n we can bring out front. What else can we bring out front? The 1/2. So the formula, the trapezoidal rule, is going to say this. It's going to say the area under the curve is approximately equal to b minus a over 2n. You see where that comes from, right, guys? Times a sum. Let me just write it that way. Okay? Now I want to show you what the sum is. Here's the sum. Okay, this is just the explanation I just gave you. Ah, there it is. Here's the sum. See, they have the b minus a over 2n out front. You guys with me? And then they have, look at this line here, f of x0 plus f of x1, and then they have plus f of x1 plus f of x2, plus f of x2 plus f of x3. If you notice, if you look at the last line, everything has a coefficient of 2, except for the first one and the last one. That's right. Does that make sense to people? No. Yeah. F of x0 plus 2f of x1 plus 2f of x2 plus dot 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 plus 2f of xn minus 1. The only things that you don't have doubled up are the first and the last. And you might say, well, why is that, Paul? And I'll say, look, see my trapezoid? We said that's using xi and xi plus 1. Are there any other trapezoids that use xi as one of the bases? Sure. Let me draw it. This one. Right? Every base gets used twice except for which one? The last one and the first one. So that's the trapezoidal rule. And that's the formula that you use to compute. So this is actually pretty interesting. Let me go ahead and show you an example. There it is in your book. Oh, it says, moreover, as n approaches infinity, the right-hand side approaches the value of the integral. That's because it's a Riemann sum. What kind of sum? A Riemann sum. It's a function evaluated at a certain point of each interval. I guess what you're really doing is kind of using the midpoint. So let n equal 4 so that we can actually do it by hand. That's what I'd have to give you on your test. It's something really small, right? You don't even have calculators when you're here. So let us approximate the value integral from 1 to 2 of x squared dx. This is a good problem to do. Let me go ahead and try it. So again, I want to compute. One of the great things about this is you can check if you're right or how close you are, right? You guys could compute that in no time. So the picture is, let's see, it goes through 1, 1 and 2, 4. There's the curve. And so what I'm doing is I'm trying to approximate this area by dividing up into four trapezoids. Does that make sense to people? So I'm going to say that this area is approximately equal to, well, let's see, what's b minus a? That'd be 2 minus 1 over 2 times, what's n, guys? 4, okay. Times some infinite, not infinite, some finite sum, some sum. And so what do I need? F of x0. Do you guys know what that's going to be? What's the first point, the first x value we're going to have? 1, right? What's the last point we're going to have? 2, right? It goes from 1 to 2. Here's the telltale sign if you know what's going on. What's the second point going to be? 1.25. Is that okay? So we're going to have, let's see how this works. We're going to have f of 1 plus 2 times f of 1.25 plus 2 times f of 1.5 plus 2 times f of 1.75 plus just f of 2. We won't double that one. And so if I compute that sum, I'll have it. So let me see what that looks like. The coefficient out front is 1/8. Now how do you compute f of 1? Yeah, it's just 1 squared. And then I need 2 times 1.25 squared. And I need 2 times 1.5 squared. And I need 2 times 1.75 squared. And then I need, well, 2 squared, right? So that's what I need to compute. Okay, let's use our calculator at this point. So let's see. 1 squared plus 2 times 1.25 squared plus 2 times 1.5 squared plus 2 times 1.75 squared, and then at the end just plus 2 squared. That's the big sum. That's not the answer. That's 18.75, right? But then what do I have to do? Sure, let's divide by 8, and I got 2.34375. So this is 1/8 of 18.75, which is 2.34375. Is that close to the right answer? What's the right answer? Anyone do it? No. Thanks, guys. Really appreciate it. Because we could have, right? We could have computed the exact value. The exact value, we'd do 1/3 x cubed from 1 to 2. So I get 8/3 minus 1/3 is 7/3. What's 7/3? 2.3 repeating. Right? I have an overestimate. Does that make sense to you guys? Why would it be an overestimate? Yeah, it's concave up, so do you see how each trapezoid is going to be a little bit above where you want to be? That's kind of cool. If what? Simpson's rule is like the trapezoidal rule, but it's more accurate in general. Okay? So maybe let's see how that can be. Let's do the same example we just did, but let's do Simpson's rule. Okay? So I'm going to go ahead and do that. I'll show you how to use Simpson's rule. Let me write it down on the paper. Okay? So Simpson's rule says, and then I'll use it, that the antiderivative, the integral from a to b of f of x dx, is approximately equal to b minus a over 3n times, well, in our example, it's going to be, well, it's f of x0 plus 4 times f of x1 plus 2 times f of x2 plus, and then it keeps alternating, 4 times f of x3, and then at the very end, you want f of xn again, just like before. But you're going to alternate 4, 2, 4, 2, 4, 2, until you get to 4, and then you finish. Okay. Now, one of the things about Simpson's rule is that to use it, n must be even. And we'll see why once I explain it, I think. But at least we could do the same example we just did, right? So let's take x squared dx, and let's try to use Simpson's rule on it as we go from 1 to 2 again. So let's do the same problem. See what we get. So again, that'll be approximately equal to 2 minus 1 over 3 times 4. So f of x0, isn't that 1 squared, right? Plus 4 times what? 1.25 squared. What comes next? There it is. And then 4 times 1.75 squared. And then, so 2 squared, which is 4. Okay. So it's funny, to do this problem, I'm just going to take my calculator and I'm going to pull the same thing up and just change some of those 2's to 4's, and I'll have it, right? So let's see. Second entry, second entry. I got back what I had before. The only thing I need to change is I need to change a couple of these 2's to 4's. Oh, and then there's one other thing I have to change, right? So when I do this, that ends up equaling 28. But now what do I have to divide by? By 12. Hey, check that out. That's pretty accurate, huh? That's actually exact. Well, I know it doesn't. I know it calculated exactly, but that's because I know what it did. I understand what Simpson's rule does, and I'm going to try and see if I can explain it to you. So in this case, it actually works exactly. In general, it should be a better approximation than the trapezoid rule. And here's why. The idea behind Simpson's rule, well, okay, there it is. It's this theorem from your book, okay? Now, I don't know that I want to prove it because, well, there's only so much time. But let me ask you, what is it we're computing the integral of here? Yeah, what shape is the curve? It's a parabola, all right? Now, let me show you the picture behind Simpson's rule. Well, again, we did x squared. So, you know, it was a parabola, okay? Now, and we split it into 4 pieces, right? Okay. The idea behind the trapezoidal rule, let me go through that again, is you take consecutive points and connect them by what? A diagonal line. The idea behind Simpson's rule is this. You take 3 points in a row and you fit a parabola like that. Then you take another 3 points in a row and you fit a parabola. And you take another 3 points in a row and you fit a parabola. Now, because this is y equals x squared, the parabolas are going to fit exactly. Okay? But in general, fitting parabolas does a little bit better than not. Okay? What's that? Yeah. Well, I mean, that's what this whole chapter's been about, really. So that's kind of cool. I like this, man. He's out of here for a minute. All right, so let me see. Here are formulas that tell me how much error I will get using these rules. I'm not going to prove that these formulas work, but it's good for you to see them to understand that we actually know how far off we're going to be when we use one of these rules. Okay? Yeah, actually, see, we know the error for the trapezoidal method. Let me go ahead and do it for the example we did. If I can do that in a minute, and I can do the other one in a minute, and Mike will be really happy then. All right, so b minus a, here's the error function. It's on page 315 also. So the error behind the trapezoidal method is less than or equal to b minus a cubed over 12n squared times the maximum value of the absolute value of f double prime of x. What a beautiful formula, huh? All right, let's use it. How the heck do we use it? Well, what's b minus a? Oh, beautiful. So this is, so the error of the trapezoidal method for our example is less than or equal to 1 over 12 times, what's n? 4. Okay, so 4 squared 16. That's right. Times the maximum value of, now do you guys know what the second derivative is? What was the function? The function was x squared. So what's the first derivative? So what's the second derivative? Beautiful. Now normally, you'd have a function here, and you'd have to say, well, what's the maximum of that function? Well, you take the, yeah, we know how to find maximum. Let's put it that way. But here, I know what the maximum value is. It's 2. So what I'm saying is, the error is less than or equal to 1 over, you said this is 192, Khalil? Okay, times 2. So let me compute that. Yeah, 2 divided by 192. The error is less than 0.01. And actually, I remember that. It was close to it, right? Instead of 2.33, it was around 2.34. Remember that? That's how far off we were. Now, what about when we did Simpson's method? We had no error. Do you know why? Yeah. But also, look at the formula. Which derivative do you need for Simpson's rule? The maximum of the fourth. What's the fourth derivative of x squared? It's 0, right? Because think about it. X squared, 2x, 2, then what's the derivative of 2? And what's the derivative of 0? 0. So at that point, there's no error. So basically, Simpson's rule, anything cubic or less, there's going to be no error. All right, we're out of here on time.